In 1981, the BBC set out to put a computer in every British school. With a challenge so urgent, a tiny company raced to build the BBC Micro in just 3 days. This wasn't a gadget, but a national mission to teach programming to millions. Why did Britain risk everything on one machine? And how did a marathon sprint at Acorn Computers change classrooms, careers, and the future itself? Monday morning, Cambridge, 1981. The BBC's requirements land on Acorn's desk, a specification both ambitious and unforgiving. The Proton, Acorn's next-generation project, exists only as sketches and scattered parts. The BBC's procurement team wants a working prototype by Friday. Steve Ferber, hardware engineer, and Sophie Wilson, programmer, know what's at stake. For 3 days and nights, the Acorn team wire wraps, solders, and codes, fueled by instant coffee and adrenaline. Each wire is placed by hand. Mistakes mean hours lost. By Wednesday night, the board refuses to boot. Thursday brings frantic troubleshooting. Wilson and Ferber trace faults through a maze of wires, improvising fixes with resistors and logic chips scavenged from other projects. The hours blur. At dawn on Friday, the prototype finally springs to life. The BBC team arrives that morning, John Cole and Richard Russell among them. They expect a Z80-based machine, but Acorn's 6502-powered Proton not only boots, it runs a demonstration in BBC Basic. The machine's graphics, expandability, and modular design surpass every expectation. The tube interface, added at the last moment, promises CP/M compatibility, answering the BBC's call for flexibility. Acorn's rivals, including Sinclair, fail to deliver a comparable system. The BBC's decision is swift. Acorn secures the contract in mid-March 1981. The Proton becomes the BBC Micro. Released later that year, it carries the title Released 1981, Maker, Acorn Computers Limited. Purpose: BBC Public Computing Initiative. The next challenge is software, specifically the language that will teach a nation to code. Sophie Wilson began writing BBC Basic in late 1979, long before the BBC Micro even had a name. Her goal was clear: create a language powerful enough for future programmers, yet simple enough for a classroom of beginners. She drew on her experience with Acorn's earlier Atom Basic, but BBC Basic would go further. Structured programming, rare in home computers, came built in, with features like procedures, functions, and the repeat until loop. Variable names could be as long as needed, not just a couple of letters. Floating point math was handled quickly and accurately, all coded by hand in 6502 assembler. Every BBC Micro shipped with BBC Basic living permanently in ROM/M. That meant the instant a machine switched on, the language was ready. No tapes to load, no disks to hunt for. Teachers could walk into a lesson, type a line, and see results at once. For many, the first program looked like this. 10 for I equals 1 to 10, 20. Print hello. 30 next I, a few keystrokes, and the screen filled with words. This immediacy wasn't just a convenience, it was a teaching revolution. Students could experiment, make mistakes, and learn by doing, all in real time. BBC Basic's tokenized storage kept code compact and fast, while its built-in assembler let advanced users write machine code right alongside their basic programs. Wilson's language, shaped by BBC editorial input and classroom needs, became the backbone of the computer literacy project. It taught students to think in algorithms, not just commands, and encouraged habits that would last a lifetime. In interviews, Wilson recalled the pressure and the pride. "We wrote BBC Basic so it would teach both the absolute beginner and the ambitious student who'd go on to write games or business software." Model B, the flagship of the BBC Micro range, arrived in late 1981 priced at £335. At its core sat a 2 MHz MOS 6502 processor, a chip chosen for its balance of speed, affordability, and ease of integration. Backing it was 32 kilobytes of RAM, a generous amount for the era, and enough to run complex programs, support rich graphics, and allow for classroom multitasking. This memory could be expanded further, future-proofing the machine for more demanding software. The Model B's architecture was designed with versatility in mind. 8 screen modes offered a spectrum of options: crisp text for lessons, high-resolution monochrome graphics for plotting data, and multicolor displays for more interactive programs. Mode 7, a teletext-compatible display, delivered sharp text while using just 1 kilobyte of memory, ideal for educational broadcasting and conserving precious RAM for code. Connectivity set the Model B apart. Standard ports included parallel printer, serial RS-423, cassette interface, and a user port for hardware projects. The 1 MHz bus opened the door to add-ons like floppy drives and analog-to-digital converters for science experiments. One of the most forward-thinking features was the tube interface, a high-speed connector allowing a second processor, such as a Z80 for CP/M compatibility, or later an ARM coprocessor, to be plugged in. This modularity meant the BBC Micro could adapt to new tasks, from running business software to powering experimental research. The Model B's robust hardware and expandability made it the backbone of school computer rooms, setting the stage for both collaborative lessons and the emergence of ambitious software, including the games that would soon push the system to its limits. By the mid-1980s, the BBC Micro was no longer a novelty in British schools. It was a fixture. In classrooms up and down the country, rows of Model Bs hummed beneath fluorescent lights, each one ready for the day's lesson. Teachers rolled trolleys stacked with computers into ordinary classrooms, plugging each machine into a tangle of power strips and coaxial cables. For many students, the BBC Micro was their first encounter with a real computer, not just a machine behind glass or on television. Morning routines often began with a login prompt. In schools equipped with Acorn's Econet network, up to 254 machines could be linked together, allowing teachers to distribute assignments from a central file server or collect students' work at the end of a session. Floppy disk drives whirred as programs loaded in seconds while the parallel port printer rattled off pages, sometimes a queue of student programs, sometimes a class newsletter designed in BBC Basic. Lessons moved beyond rote typing. Teachers demonstrated new concepts on their own BBC Micro, projecting the screen or printing out code for discussion. Pupils worked in pairs or small groups, experimenting with graphics commands, plotting graphs and saving their efforts to disk. The classroom became a workshop, with students building everything from simple quizzes to data logging experiments using attached sensors. The scale of this adoption was unmatched. By 1985, more than 80% of UK schools owned at least one BBC Micro, and many had entire labs. The machine's reliability and expandability made it a natural hub for collaborative learning. For teachers, the combination of instant-on-basic, reliable disk storage, and networked resources meant lessons could be planned around creativity, not technical hurdles. For students, the BBC Micro was more than a tool. It was a gateway to a new way of thinking, and often the first step toward writing their own software. Elite, released in 1984 by David Braben and Ian Bell, pushed the BBC Micro to its absolute limits. With just 32 kilobytes of RAM, Braben and Bell fit an entire universe of star systems, wireframe 3D graphics, and real-time trading into memory that could barely hold a short story. Their code squeezed every cycle from the 2 MHz 6502 using clever data compression and procedural generation. Elite sold over 60,000 copies in its first year, launching a new genre and inspiring countless young programmers. Repton, created by Tim Tyler, became a household name for its puzzle-driven gameplay and inventive level design. Tyler built intricate maps and logic into a tiny memory footprint, letting players create and share their own challenges. Chucky Egg, with its fast, tight controls and addictive platform action, became a staple of break times and after-school sessions. Each of these games proved the BBC Micro was more than a classroom tool. It was a playground for invention. Decades after its launch, the BBC Micro's influence still echoes through classrooms, museums, and online communities. Former pupils often credit their first lines of code on the Micro as the spark that led to careers in software, engineering, or digital arts. Today, the machine is more than a memory. At the Centre for Computing History in Cambridge and the National Museum of Computing at Bletchley Park, Restored BBC Micros hum quietly, running original programs for new generations. Enthusiasts gather at retro computing events, sharing stories and demonstrating hardware once considered obsolete. Online, emulators and archives keep the platform alive, letting anyone experiment with BBC Basic or explore classic software. These efforts preserve not just the hardware, but the spirit of discovery that defined a generation of British programmers. By the mid-1980s, over 80% of UK schools had a BBC Micro in their classrooms, a direct result of the BBC's 1981 computer literacy project and Acorn's rapid development. The BBC Micro's technical strengths, such as its 2 MHz 6502 processor and built-in BBC Basic, enabled both structured learning and a surge of creative projects, including landmark games like Elite and Repton. Yet, some BBC internal files on procurement decisions remain restricted, and the full impact on individual career paths has never been fully traced. Today, museum exhibits and active online communities keep the BBC Micro's legacy visible, while emulators make its software accessible worldwide. The evidence shows the BBC Micro was more than a machine. It was a catalyst for digital skills in the UK, its influence still felt in classrooms, code, and the memories of a generation.